We'll discuss Kruskal's minimum spanning tree algorithm in this video. A spanning tree is simply a tree that connects all the vertices in the graph, and when there are edge weights associated with the edges of the graph, a minimum spanning tree is simply the spanning tree that has minimum weight. And the weight of a spanning tree is simply the sum of all the weights on its edges. So Kruskal's minimum spanning tree algorithm is a greedy algorithm. It takes local decisions, and based on the local decisions, it arrives at a global solution. Now the idea is basically to maintain a forest of trees, that is a collection of trees, and progressively introduce new edges in the forest so that trees get merged, and eventually at the end of the algorithm you get a single tree, which is the minimum spanning tree. So there are two things to be done in Kruskal's algorithm. Basically, at every step we have to figure out what is the minimum weight edge that is available for addition to the forest, and so the mean weight edge that is available for addition in the forest. And second, we have to ensure that when we add an edge, it shouldn't introduce a cycle, because if you introduce a cycle, then a tree is no longer a tree. So no cycles when we introduce an edge. The way information is maintained are based on this. First of all, to know what is the minimum weight edge that is available right now, what we can do is we can sort all the edges according to ascending order. Sort the weights, rather, the weights of the edges according to ascending order. And from that ascending order, we can pick an edge at every step when we need to choose an edge for adding to the forest. So this is the first thing. And second thing, what we need is, given an edge, basically an edge is nothing but a pair of vertices, we have to quickly determine whether those two vertices are they belong to the same tree or they belong to the different trees. If they belong to the same tree, we can't add that edge because that will introduce a cycle. So we have to ensure that the end vertices of an edge belong to different trees. So for that, what we do is we keep some sort of information for every vertex that is in our forest. We keep a parent information. The parent in the sense that whichever tree that vertex belongs to, the whole tree is represented by one of its vertices. And if we can quickly find out, okay, I am given vertex u, and this vertex belongs to this tree. I am given vertex v, which is the u and v are the two endpoints of an edge, and v belongs to a different tree. And if that condition is true, then we can introduce the edge uv. So that is the parent information or representative information for every tree that we have to maintain. So before going into that a little bit, let us see how it looks like. For example, suppose this is a tree in the forest called T1, and this is another tree in the forest called T2. And when you merge these two, for example, let us say this is vertex U, this is vertex V, we have to introduce this edge UV, and you can see now the overall structure T1 union T2 is another tree, and we have effectively increased the size of one of our trees. And that's the whole idea. Go on increasing the size of the trees, and eventually at the end of the algorithm you will have a single minimum spanning tree. Now the parent information, that is what we have to take care of. So let us call this is one of the trees between vertex 1 and 2. This is vertex 4, 5, and 6. As before, suppose we are merging these two vertices. As I told you, for every tree we keep a representative of the tree. So for example, for tree T1 and for tree T2, let us say the representative for T1 is the vertex 1 and representative for T2 is the vertex 4. What it means is we can basically define a parent function where I say parent of 1 is 1, parent of 2 is 1. What it is saying is basically that both 1 and 2 belongs to the same tree. Similarly, here you can write parents of 4 equal to 4, parents of 5 equal to 5, parent of 6 equal to 6. In other words, no, that's not correct. Parent of 5 and 6 both are 4. In other words, all the vertices in this particular tree or this particular set, they belong to the same tree or same set whose representative is the vertex 4. Now if I have a query, okay, I want to add an edge 1, 5, namely the edge that I have shown here. Now for adding this edge, I have to make a query, who is the parent of 1? Immediately from here I can tell it is 1. Who is the parent of 5? Immediately I can say it is 4. So when we know that the parent of 1 and parent of 5 are different, so they belong to different trees, and I am safe to add the edge 1, 5. So how do this parent information, how do we maintain this parent information? Basically the parent information is maintained as I have shown before, 1, 2, let us say 4, 5, 6. But when I am introducing this edge, I have to somehow combine these two sets, right? So for example, earlier the parent of 4 was 4, parent of 5 was 4, and parent of 6 was 4. Somehow I have to update to all of this parent information to make them 1, because let us say the parent of the combined tree is 1. So how to do that? One way of doing that is just go through each vertex and change their parent information from 4 to 1, which is possible but which is inefficient. So what instead is done is simply you connect the root of the second tree to the root of the first tree. So this is 4, 5, 6. So when you have connected like this, then what I can do is, if in future I have a query that I am trying to add an edge between vertices 2 and 6, so I have to answer this query, who is parent of 2? I know immediately from beforehand, nothing has changed here, that parent of 2 is 1. And now the other question is, who is parent of 6? Now what I can do is I can traverse from 6 and go up and up and up, and once I hit the root, I know parent of 6 is 1. So I know both parent of 2 and parent of 6 belong to the same tree. I cannot add this particular edge between 2 and 6, because then that edge will introduce a cycle. So it looks quite bad, doesn't it? I mean, basically what is happening here, as we connect the parents of old trees to existing trees, just as we have connected 4 to 1, I may connect other trees and so on, and it may grow very, very long and skinny. So you can say that, okay, to figure out the parent information, I have to traverse very long paths to reach the root and answer the question, who is the parent of this node U? The answer is yes, you are right. But what is needed here is an amortized analysis to determine what really is the cost of such traversal. And actually what is done is, such a traversal is another heuristic is introduced, which is called path compression. What is path compression? basically when you are traversing such long paths, what you can do is you are anyway touching all these vertices along the way. So you can directly connect all those vertices to the root of the tree after the traversal. And what is happening now? You can see the meaning of path compression. Basically, all these long paths are now broken up and made very small one-hop paths because they are directly connected to the root of the tree. In future, if I have a query for this node here, for example, I don't need to spend any long time for traversing it from here to the root, because after the first traversal here, this node will become a direct child of the root because I have connected it directly to the root. So in a way, when you are doing some extra work here, you utilize that extra work to reduce future work. And the future work is parent query for this node. So this heuristic is very powerful. We can't analyze the complexity of this heuristic in this unit because it's quite mathematical. But I can say that the complexity of the find operation is simply the parent query. Another name is the find operation. Who is the parent? Find it. So that find operation has a complexity of log star v, which is a very slowly, where v is the number of vertices in the graph. This is an amortized complexity. So even though sometime you will do a lot of work, but on an average you will do very little work. Log star v is an iterated logarithm which has very low values. It's a very slowly increasing function. So what is the overall complexity in Kruskal's algorithm then? Remember or recall that every edge I have to examine, right? Because when I am trying to merge two trees, or I am trying to introduce a new edge, I have to look through which is the minimum weight edge, whether it forms a cycle. So in effect, over the execution of the complete algorithm, you have to look at every edge. And the amortized complexity of looking at an edge and finding the parent of the endpoints is log star v. So overall complexity of Kruskal's algorithm is E log star v.